Hi guys, Dr. B here. This is your lecture on how to do Lewis dot structures using the V's up method. One of the things you need to remember how to do is how to do your Lewis dot structures. Remember they're based on the number of valence electrons. So let's review these really quick. So aluminum has 3 dots. Bromine has a total of, let's do a different color, I guess, 7. Boron has 3. And you know that just by looking on the periodic table for them to get a full valence shell. Carbon has 4, and fluorine has 7. So when we're looking at these Lewis dot structures, you see that some of the way they've been written, for example, here we have like that, sorry, it should be a different color, that, or that. Those are called lone pairs. So normally, I say normally, but usually they do not get bonded with at this level of chemistry. We're going to see, however, in our notes that it can be possible, but for the most part, no. They don't really bond with anything else if they're already in a lone pair. So that's something to be mindful of, and also be mindful of how many valence electrons are possible. So for example, if you have a hydrogen, it can only have 1 valence electron. Okay, that's important because it can't have a full octet because it can't make one. Boron only has 3 valence electrons, so it can only share with 3 other electrons to make, to form its bonds. So I'm going to introduce now that whenever you see, for example, when we do these Lewis dot structures, we did them for just the elements with the dots. Now we're going to do it for actual covalent compounds. So forewarning, you're going to see something that may look like this, or some other type of non-metal. Whenever you see a bond or a line between 2 elements like that, that is actually 2 electrons that are being shared. We're going to also discuss it if you see 2 bonds like a double bond like this between 2 elements. Well, actually, that wouldn't happen. So let's say like that. That's 4 electrons being shared. That is 6 electrons being shared. So you have 2 electrons being shared, 4, and then 6. So again, how are covalent bonds formed? They are formed by nonmetals. What is it between? It's between nonmetals, and they are sharing electrons in order to sharing their valence electrons in order to obtain a full valence shell. So how are they formed? What is it between? What are the elements involved trying to do? They are nonmetals that are sharing their valence electrons to have full valence shells. So how do you do it? So it's called the V's up method. So V's up stands for the valence electrons, your skeleton structure, how many are used, and we're going to see what that means, and the lone pairs of electrons, or the lone electrons. So these other steps here, I know it's a lot, but you have to be, I'm going to go through a bunch of examples, so it should be fairly easy to follow, and I will hit on these as we go through the examples. So I won't say these right now because we'll get there when we get there. Okay, so the first one is CO2, or carbon dioxide. You shall also know how to name these as well. So I'm going to put the name actually, then might as well then. Carbon dioxide. So V's up. So the number of valence electrons, which is going to be 4 from carbon plus 2 times 6, a total of 16 valence electrons. Now we're going to draw out the skeletal structure. So the less electronegative elements or the single elements are most likely going to be in the center of your Lewis-Dot structure. So we have carbon, it is less electronegative than oxygen, and it's only 1, so that makes it easy on us. So we're going to put that in the center. Remember, though, that these are valence electrons. Sorry, these are electrons, so they're going to want to repel from each other. So I'm going to draw a bond here and here as far as I can, because that's now the only other elements I have to work with. There's 2 oxygens. So I've used up a total of 1, 2, 3, 4 electrons. I'm going to subtract now the 2 numbers. I end up with 12. So now I'm going to put 12 valence electrons on my skeletal structure for my Lewis-Dot structure. I start from the outside elements and work my way towards the middle. So I have 12 to deal with. If you want to think, oh, I have 12, and then for it's a pair, I have a total of 6 pairs of valence electrons to put, you can do that too. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you may think we're done, but we're not. You have to now look, do all of my elements have a full valence shell? And can I move electrons around somehow to do it? So both of my oxygens do, but my carbon only has 4, and it likes to have its 8. So what we're going to do is, to continue with this, we are actually going to take these electrons, not take them, but circle that. So here, this is actually going to now become a bonded, a double bonding that side. I'm going to do the same thing over here. And then now, I'm going to rewrite this to make it nicer. But we have a carbon double bonded with oxygen on either side. Don't forget your lone pairs of electrons. Remember that electrons want to repel from each other because they have the same charge. And now we're done. You don't have to box this because it gets kind of messy, but be sure you're organized. If not, if I can't read it or it gets too messy, then I'll just mark it wrong. BF3, so this is boron trifluoride. So V's up. Sounds like fangs up, but it's V's up. So valence electrons, I have 3 from boron plus 3 tri times 3 from 7 from fluorines. That's a total of 24. Now I draw my skeletal structure. Boron in the center. Put my 3 F's surrounding it. Remember, they want to be as far from each other as they can. And this is going to lead into something we're going to talk about later on in this unit. I've used up 6 electrons, so I subtract that, end up with 18. Now I'm going to put these 18, or my 9 lone pairs, around on the outermost elements. And remember that boron can only form up to 6 bonds. I'm sorry, 3 bonds, I'm sorry. So then now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. And boron has its limits, so we're good. Next is ammonia, or NH3, nitrogen trihydride. If you Google the name of NH3, it will tell you ammonia, and that's fine, because that's true. But you should be able to determine the scientific name, the chemical name, not just the common name if it has one. So V's up. Valence electrons, 5 from nitrogen plus 3 times 1 is 8. Have your skeletal structure. I've used up 6 electrons, so I have 2 electrons left, or I have 1 lone pair left. Remember though that hydrogen cannot have more than 1 valence electron, or if it's bonded it will have 2. So the only place I can put these are on nitrogen. And remember, nitrogen has a Lewis dot structure like this, with its 5 valence electrons. So if you want to think about it, hydrogen has 1. It's going to share these 2 electrons now. Oops. Form its bonds. So same concept. So think of it as a puzzle if you need to think of it that way. But remember how many valence electrons these have. We need to know that. You need to know what if there's a limit to how many bonds they can form, etc. CS2, CS Lewis, CS2 carbon disulfide. Excuse me. Reads up. 4 plus 2 times 6, 16. Skeletal structure. Carbon, sulfurs on either side. That's all the elements I have to work with. So I've used up 4, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm going to take this lone pair and put it here because my carbon only had 4 electrons that it had. So now let's look at this. So you have carbon double bonded with an S on either side, and you have your 2 lone pairs on either side. So that's it. Sulfur hexafluoride. So this is kind of an exception, but you should be able to figure this out just by using the V's up method. V's up. So remember that sulfur has, you should know that it has 6 valence electrons. So let's see, so sulfur is 6 plus 6 times 7 from the fluorine. That's a total of, 48. Skeletal structure, sulfur, and then I have 6 fluorines I can put around this. So I've used up 2, 4, 6, 8, 10, 12 valence electrons. I have 36 left over, or 18 pairs. Hopefully this works out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. There we go. So I said it's kind of an exception because remember, well, these are lone pairs, so we don't mess with those. And you're right. That's how it usually is, particularly at this level. However, phosphorus, sulfur, chlorine, what they can kind of do actually is form an expanded octet, and that's outside the scope of this class, but it is the reason why this particular element is able to form bonds elsewhere. Not elsewhere, but form bonds also with its lone pairs. It's called an expanded octet. We won't cover that really, but again, you should be able to figure out the Lewis dot structure based on this method. All right, the last one is carbon tetra. Oops, carbs. Carbon tetrachloride. Ooh, man, ugly. Okay, so V's up. You have 4 valence electrons plus 4 times 7. The chlorine, that's a total of 32. Skeletal structure. Carbon in the middle. CLs. Yeah, 4 CLs all around. That's it. That's all I have to work with in my skeletal structure. You have 8 we've used up. So a total of 24 electrons left to put in. So carbon already has its 2, 4, 6, 8, so it doesn't really can't really have any more. So most likely my lone pair electron should just be on the chlorines. But let's just double check. 1, 2, 3, 4, 5, 6. Oops, can't see that. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Well, there we go. Not too bad, not too bad. All right, well, that's it for now. Let me know if you have any questions. Okay, thanks. Bye.